Hello everyone. In this video we'll learn about an important concept in the time domain response, which is the steady state error. We have already seen in the time domain response that for a closed loop system where RFS represents your input signal, C of S is your output signal or response, G of S is the loop forward path loop and forward path loop gain, and H of S is your feedback path gain. Then once you sense your output C of S through the gain feedback path, the signal that reaches your signal multiplier is Cs into Hs, and it is shown as a negative feedback, and E of S is known as the error signal that is being generated. So your E of S is basically R of S minus Cs into Hs. Okay, so this E of S is in Laplace domain. When I take the inverse Laplace transform, I get my error signal E of t, and steady state error is the value of error signal E of t when t tends to infinity. The output signal C of S can be got as also expressed as the product of your error signal and the forward path gain. So E of S into G of S gives you the C of S. Now substituting my C of S as Es into Gs and taking all the E of S terms to one side, I get my expression E of S as R of S by 1 plus GSHs. As you can note that this plus comes because we've given a negative feedback. So finally your E of S is R of S by 1 plus Gs into Hs. And as I said, I need my error signal time domain. So taking the inverse Laplace transform, I'll be getting my E of t. So if I represent ESS as the steady state error, then steady state error is defined as the value of E of t when t tends to infinity. So it can be expressed mathematically as ESS is equal to limit t tends to infinity E of t. Now we have already learned the final value theorem in Laplace transform, which says that if f of s is equal to Laplace of f of t, then your limit t tends to infinity, f of t is equal to limit s tends to 0, s into f of s. So I am going to apply the final value theorem on this, and hence I can express my steady state error ESS as limit s tends to 0, s into E of s, where I have substituted my E of s. So basically it can be written as limit s tends to 0, s into R of s by 1 plus Gs into Hs. We'll have a look at the few of the features of steady state error. As you know, it is a measure of your system accuracy, because error signal is what? The difference between your actual output and desired output. So based on that you can measure your system accuracy. And ideally, as you know, the system reference input should be matching with it. So when this E of t is equal to 0, you get your ideal scenario, which means you don't have any error in your system. So for an ideal case, we can say that the steady state error should be as low as possible, and therefore this ESS is an important performance measure of any control system. Steady state errors basically depends on two factors. You can see from the expression that E of S is equal to R of S by 1 plus GSHs. So it depends on two factors. One is the type of the reference input that you give, and we have already had a look at the in the previous module, the standard test signals, step, ramp and parabolic. So it depends on what is the type of the reference input, and it also depends on the type of your system, that is G of S. H of S may be in most of the cases unity, so it is not expressed as that. And steady state errors are calculated only for closed loop stable systems. Okay, only for closed loop systems. Thank you.